Hi, everybody. My name is Isaac Lyngaas. I'm a postdoc at Oak Ridge National Lab, and today I'm going to be presenting, like she said, the work I did porting the cloud resolving model, CRM, using E3SM multi-scale modeling framework to perform its portable C++. This is work I've been doing alongside my postdoc advisor, Matt Nolan. I'll begin now with a brief introduction, for a brief outline of my talk. I'll begin with a brief introduction to E3SM, MMF, and SAM, a system for atmospheric modeling, which is the CRM used within E3SM, MMF. Particularly, we want to motivate the approach, including the ability of it to utilize accelerators to speed up computation. We will then talk about limitations and previous efforts of porting SAM using an open ACC directive-based approach. Following that, we'll go through our approach to port SAM to performance portable C++ using YAKL performance portable framework that is utility especially made for porting Fortran to C++. We then will look at some computational and performance porting results from this work. So E3SM is DOE's high resolution climate model, originally forked from CESM. It is modified specifically to be optimized for performance on supercomputing systems. Our work is specifically focused on the atmospheric portion of E3SM, where the traditional E3SM atmospheric model uses a spectral element dynamical core to simulate the dynamics. In order to simulate moist convection, traditional E3SM resorts to using a parameterization scheme to account for the effects of clouds. This choice is specifically made because it's too expensive to include a full cloud model due to the fine resolution that is needed to explicitly resolve the effects. The E3SM multi-scale modeling framework replaces this parameterization scheme with a high resolution cloud model at each global model column. These CRMs use much higher resolution than the dynamical core near 1 kilometer grid spacing. We use SAM as the CRM for E3SM MMF. SAM is used in E3SM MMF to simulate convection in either 2 or 3D at each grid column. This simulation is used in tandem with the global model, which nudges the CRM mean state, and in turn, the CRM provides forcing for the moist convection variables. The need to calculate CRM introduces computation that is 100 times the amount in traditional E3SM. The MMF approach provides a middle ground between the traditional E3SM and a model resolved at a 1 kilometer grid spacing globally, which would take approximately 22,000 times more computation compared to traditional E3SM at 28 kilometer resolution. The key to the MMF approach is that the CRMs not need to communicate. So the traditional E3SM model introduces parallelization to multiple CPUs using MPI. And in large production runs, it becomes heavily bottlenecked with latency dominated MPI communications. Through the addition of the CRM calculations in the MMF approach, we're able to add in computations that do not add to this already large amount of MPI communication and is particularly in a good state to utilize previously unused accelerator devices on systems that have them. The goal of the MMF approach is to better resolve the effects of cloud than the traditional approach in a similar time frame by using accelerators. So both E3SM and SAM are exclusively Fortran-based codes that utilize MPI for parallelization. Recent work has been placed into porting SAM to Fortran OpenACC code to launch on GPUs. However, these efforts, these efforts included a refactoring of the code to run multiple CRMs each time. At each time the CRM function is called, in order to increase the computational density of the kernels within the code, exposing more parallelism, and including the introduction of atomics and reductions for code correctness. Although this port was successful, there was found to be limitations with the OpenACC Fortran implementation. These issues have to do with the dependence on the compiler that the directive-based approach. Specifically in implementations within E3SM, bugs were ran into which forced the use of CUDA managed memory and without a memory pool allocator. And this caused poor performance in the application. Some other limitations include the speed at which these directive-based approaches are available for new architectures, and the different compiler interpretations of standards, which limit portability. These factors lead us to the need to port the Fortran SAM code to a performance portable C++ framework. So in order to do this, we chose to use YAKL, which is a simple C++ framework for portability, and Fortran Code porting developed by Matt Millman. This porting framework uses a Kokkos-like interface with all the necessary utilities for porting to accelerators. The reason we choose this particularly is its simplified form and its Fortran utilities. In SAM++, we mostly take advantage of YAKL's Fortran bindings to C++ memory allocators, which is crucial for the porting process. One nice feature of YAKL that didn't exist at the time that we did this port was the ability to handle some Fortran intrinsic functions such as array slicing and handling of non-standard lower bounds to arrays. I won't go too much more into detail as Matt is going to be presenting on this tomorrow. All right. So the first steps in porting the code include isolating SAM and E3SM from E3SM MMF into a standalone framework. So we don't have to run all of E3SM every time we want to test our ported code. Also, we gathered data from a number of runs from the existing version of E3SM MMF to use when doing porting correctness testing. We then create a build system in a script, which runs both the base Fortran code and a Fortran C++ porting code base for to do porting correctness testing. We use these to incrementally add C++ functionality. This incremental approach to adding C++ functionality requires a hybrid Fortran C++ code base. So during the porting process, we take advantage of YAKL's Fortran bindings to C++ memory allocators. And so all variables within the porting code base are allocated within Fortran. However, they need to be visible to C++. So we also introduced a wrap array routine, which will be shown later. The testing that is done throughout the incremental porting is done on both a CPU and an NVIDIA GPU to ensure porting correctness on accelerators. Since we use YAKL's memory allocators, we can implement managed memory to handle hybrid CPU plus GPU computation. So in the hybrid framework, we use ISO-C bindings to call C++ code from Fortran. As I mentioned before, during the porting process, we need Fortran initialized memory. We need a type match to C++ data standards, which is easily done. From there, scalar variables can easily be used in C++ scope by simply adding a bind C clause, while arrays are passed to C++ as a pointer. So some extra work needs to be done to make these arrays usable within the C++ framework. So here's some code that shows the three types of data initializations within the Fortran code. Specifically, scalar, which has that added bind C clause, and YAKL's Fortran bindings for array allocations. So these calls allow the Fortran variables to be accessed exactly how they had before, while specifically using YAKL's memory allocator. Within SAM, and apparently a lot of Fortran applications, subroutines have minimal parameter passing. Rather, they choose to use module-owned variables, which is difficult to replicate in C++. So in our porting work, we choose to make all variables in the C++ global variables. While not top particularly good practice, this allows for the easiest form to port the code if proper care is taken. As global variables, we don't need to pass parameters to ported C++ routines and can more easily match the Fortran code without having to make a lot of changes. So here's some code we used during the port to make the Fortran variables global variables within C++. The Fortran ISO-C binding subroutine on the right passes pointers to arrays in the C code. And using a header source code pair, we wrap these pointers into YAKL global arrays. And here the YAKL global arrays are type defined. And this is to avoid the long definitions that are typically involved in performance portability framework. One thing to note about these wrapped arrays is that the array dimensions are now transposed from the Fortran allocations. So this is to account from differing array storages between C++ and Fortran. That is column major and row major. Also at the point of the port, there was no utility for non-standard lower bounds. Therefore, in order to use them in ported code, we need to handle them with offsets. Fortunately, if somebody were to use YAKL right now, there is Fortran intrinsics that will handle this for you. So with these memory initialization routines and global C++ variables, we do the porting, which is a very smooth process with YAKL for porting SAM++. And during the process, we only had to make some small adjustments in the base code. These small adjustments to make the code near machine precision differences between the base code and the ported code. Also, we have to introduce the Fortran FFT routines that are originally used within SAM because we found them very difficult to port. But these add very little computation to the overall SAM++. So here's a look at some porting correctness results between the base Fortran code and codes run on CPUs and GPUs using YAKL. During this testing phase, we found that nearly the core of the variables were bit for bit the same, and the rest we found that acceptable error between the two versions, nearing machine precision for both GPU and CPU implementations. Now look at some benchmark results using a single node of some a particular target of E3SM MMF due to its heterogeneous makeup of CPUs and GPUs. We want to determine the efficacy of the approach and the performance of the ported code on GPUs. Here in this 2D standalone run of CRMs, we see that with the increasing number of CRMs, that the GPU implementation is outperforming the current Fortran CPU implementation when fully utilizing all the hardware on the single node that we're looking at. This provides validation that the MMF approach is beneficial for accelerator usage. We only test a single node because the computations should easily scale to higher node counts, because there is no communication needed between the CRMs within a full run of E3SM MMF. Some similar results in 3D. These look a lot the same because we're using the same, instead of 64, this is partition of the CRM computations. Now we're using 8x8 in the 2D, and we're getting slightly better speed ups over the initial Fortran CPU implementation. So in conclusion, we've cleaned up this our initial port of the code, and now it's in all C++ except for the call that calls it from within E3SM MMF, and it's integrated into E3SM MMF. We found that YAKL provides a nice framework for porting Fortran to C++ with the nice utilities, and we're able to create a single source for SAM++ that can run on various architectures. Some future work that needs to be done is some testing of YAKL. And this will just be done by looking at some computational kernels within SAM, just to make sure that there's not any big mistakes going on within YAKL. I know there's already been some of this being done. Since YAKL it's kind of a simplistic framework, it's never going to be as optimized as the more mature performance portability frameworks such as like Kokkos. For future work will include porting to Kokkos for further performance improvements, which should be a simple task since it's already used some of the same syntaxes as Kokkos. All right, and thank you for your time. Some acknowledgements, and we'll get to some questions.